Hello. In this video, we introduce how to solve systems of nonlinear equations using our old methods of substitution and elimination, and even some graphing. Let's get started. So to begin, let's take a look at this chart, which basically reminds us of what happens when we have a system of equations. In the previous video, we discussed systems of linear equations, where we said two lines either intersect at one solution and we would have a consistent independent solution, or they intersected everywhere because they were really on the same line. We would have a consistent dependent set of solutions. Or, on the other hand, the two lines were parallel with the same slope, so there was never an intersection point. We would say there would be no solution and the system was inconsistent. Now, in this scenario today, in this video, we look at parabolas and lines put together, circles and parabolas, circles and circles, all kinds of mixtures of nonlinear equations, where they intersect and where they do not. So let's take a look at the picture in the middle of the slide here. We see that on the first one, in A, we have a parabola opening up, and we have a line below it with a certain slope so that it appears that the line and the parabola never intersect. We would say that that would be an inconsistent system for that reason, because there is no solution. But notice that in B, we have a parabola with a line touching it at exactly one location, at the point 2, -3. So we would say the solution there would be the point 2, -3, because that's the one and only point where the line and the parabola intersect. Then we see the third picture, C, where the parabola opening up is intersected by a line at two locations. We see that happening around here in quadrant 2 and around here in quadrant 1. So we would say at those two locations, we have our solutions to this consistent system. Now the question is, how would you determine those solutions, whether or not we have them to begin with, and what they are if we do have solutions, by just using the equations themselves, by not looking at the pictures? Well, we could apply the techniques that we talked about in a previous video with linear equations, and that was substitution and elimination. Now, I will say that elimination will only work if you can eliminate like variables. So for example, if I chose to do the elimination method on this example, where the first equation is a parabola, y equals x squared minus 4, and the second equation is a line, y equals x plus 2, if I were to try to eliminate right now, the y's could cancel if I subtracted equation 1 minus equation 2. But notice that x squared and x would not eliminate. Rather, we'd have x squared minus x, and then -4 minus 2 is -6. So you would have x squared minus x minus 6 equaling 0. And then you could go about solving that for x. But the way that most students will prefer to solve this system is through substitution. So if you went through the substitution approach, you would first look for a variable which already is isolated, or you would try to isolate one by yourself. For example, in equation 1, y is already isolated. So that means I could replace y in the other equation with whatever y equaled from the first equation. So now basically you're setting them equal. You would have, instead of y, you would write x squared minus 4 must equal the other y, which is x plus 2. Now this is a quadratic equation, and if you get everything on one side, you can solve this. X squared minus x. If you subtract 2 on both sides so that you have 0 on the right, you get -4 minus 2, or -6, which is the same thing we would have gotten using the elimination approach if we did it correctly. Now, if you can see factoring, that's always the fastest way to solve a quadratic equation like this, where you have a trinomial equals 0. Otherwise, you could use the quadratic formula where a is 1, where b is -1, and where c is -6. Go ahead and see what you got as your factors. X, what factors of -6, so with different signs to get a negative result, would add up to give you a -1, because the coefficient of x is negative. Well, you would have either 6 and 1 or 2 and 3. Those are your factors of 6. So with different signs, which of those would produce a -1? Well, 2 and 3, but what sign should I use? A -3 and a +2. That would result in a product of -6, and when I add -3x and +2x by foiling there, I get -1x. The zero product rule then would tell me, if I set each factor equal to 0, either x minus 3 equals 0, so that x equals 3, or x plus 2 equals 0, so that x equals -2. So if I wanted to understand what's going on here, we're talking about a parabola and we're talking about a line. I'll do the parabola, I'll do a quick sketch for you. I'll do the parabola in white, okay? So for this parabola in white, it's been shifted 4 units down. So it's been shifted 4 units down. You can go back and review your graphs. This is a parabola that's been shifted 4 units down. And we also had shifted 2 other points, 1, 1 and negative 1, 1, down 4 units as well. So we'd be at 1, negative 3 and negative 1, negative 3, just to get a few key points. You could also get the x-intercepts by letting y equal 0 if you wanted to get a better, more detailed sketch, but I'm just doing a quick run through. So there's a quick sketch of the parabola that's been shifted down 4 units. On the other hand, the line y equals x plus 2 would have a y-intercept of 2 and a slope of what? 1. Good. Up 1, right 1. Up 1, right 1. And you keep going. Down 1, left 1, etc. You'd end up getting something like this as your graph. So it appears just from a quick sketch that I should have how many solutions? How many times does the line appear to hit the parabola? That's right, it appears to hit twice. We would say those are called my points of intersection, or my solutions to this system. When we get to our next video, we'll be talking about shading inequalities of nonlinear systems. You'll first need to find these points of intersection using substitution and elimination before you can begin to find the shaded region for the inequality. Now, what we've just found is that when x equals negative 2, that's one of the times where the 2 graphs intersect. So that looks like in the graph, it would be like this answer on the left. And when x equals 3, that appears to be maybe over here. Because I didn't have graph paper, it's not drawn to scale. Okay, so then we say, how would we find the y component of these solutions? Well, we could either plug in the x values that we got into the first equation or into the second equation. Now, if you remember our last video, I said that when they're both lines, it doesn't matter which equation you plug this variable into. But if we're dealing with nonlinear equations, it does matter. You'll always want to pick the equation with the lower powers, because that will be the place where both of them are guaranteed to be intersecting. If you pick the one with the higher powers, that might be a point on the parabola or the circle, but it's not likely going to always be on the line, because the line is going to be more restricted. So we're going to always go to the lower powers to plug into. So let's do that. Replace x with 3 in the second equation, the linear equation. You would have that y should equal 3 plus 2. So you replaced x with 3. 3 plus 2 is what? That's right, it's 5. So when x equals 3, y should equal an output of 5. So at x equals 3, we would have y equaling 5. Now obviously my picture is not drawn perfectly because that axis should be a lot lower, that x-axis. But the idea remains the same. At some point you're touching and it looks like it's at 3, 5. What about x equals negative 2? At negative 2, you can insert that for x into the second equation for the line, and you would get that y equals negative 2 plus 2. Replacing x with negative 2. You would get 0, wouldn't you? So you have an output of 0 when you have an input of negative 2. Okay? So in this situation, we should be getting the solution of negative 2, 0, and 3, 5. And again, you can ignore the picture that is not done perfectly because I didn't have graph paper. But the idea that you had 2 solutions was something you saw happening just by doing a quick sketch of a parabola shifted down 4 units and a line whose slope is 1 and whose y-intercept is 2. In fact, I think I see what happened now. I think I did a negative 2, which is probably why that line looked a little bit off. But the solutions are the same as we just got in our picture. The solution set would be the point, for our solution set here, it would be the point where x is negative 2 and y is 0, and where x is 3 and y is 5. So again, the graph is there to kind of help you to understand what's going on if you graph it correctly, of course. You can also click on the Desmos link provided in each of your notes on the slides. Click on that link and you're going to see the actual graphed answers, and you can click where they intersect and you can compare to make sure you are getting the right solutions when you're doing your work at home. All right, let's see if we can apply this to another example. Make sure you pause the video and try it on your own. Example 1 says, solve the system if possible using substitution or elimination. For the first equation, we have x squared plus y squared equals 9. For the second equation, y equals x squared minus 3. So if you were thinking about what these graphs represent, do you recognize the patterns for these types of graphs? What would our first graph be representing? X squared plus y squared equals 9. Does that ring a bell? That one should. We expect you to recognize the graph of a circle by looking at its equation. Remember that a circle in standard form, it came from the distance formula and the Pythagorean theorem. It said x minus h in parentheses squared plus y minus k in parentheses squared equals the radius r squared. So it's directly from the Pythagorean theorem and the distance formula. That's our standard form of any circle whose center is h comma k and whose radius is the number r. So with that in mind, what is the center of my circle? Do you see it? Well, the hk is implied to be the 0, 0, the origin in this case. And what about the radius of my circle? R, well, r squared is 9, so r must be a positive distance of 3. The square root of 9 is 3. So if I were graphing a quick sketch of this circle just to see what's going on, start at the center of 0, 0, and go in every direction 3 units. 3 units up, for example, would land me at 0, 3. 1, 2, 3. So there's the point 0, 3. If I went 3 units right, I'm going to be at the location of 3, 0. So there I am at the location 3, 0. If I went 3 units down from the origin, 1, 2, 3, I'm at the location of 0, negative 3. And if I went 3 units left, 1, 2, 3, I'm at the location of negative 3, 0. Connecting those dots, in fact, I didn't need the tick marks, so just to be consistent here, I won't use them. If I draw my circle now, it would look something like this. You can probably do a way better job than me right now, especially if you used a compass and a protractor, you would have a much better looking circle than I'm currently attempting to draw for you. Okay, so a circle, again, definition-wise, it's a set of all points which are exactly the same distance. That distance is called the radius from a fixed point in the center, which is known as the center HK. Okay, so once you have a sketch with 4 basic points around your circle, let's take a look at what the second graph would look like. For our second graph here, we have y equals x squared minus 3. What type of equation is that? Only x is being squared. This is starts with a p, that's right, parabola. So some of you might need to go back and practice your basic graphs of circles and parabolas and lines, and I think that's about it for this video. That will be very important for you to get a visualization of what's going on. Okay, so let's take a look at the parabola here. How has it been shifted? If you had y equals x squared, it would just be the original parabola with key points at 0, 0, 1, 1, and negative 1, positive 1. But if you have a minus 3 here, kind of like we did in the last example on the last screen, this has been shifted down 3 units, hasn't it? It's called a vertical shift. If it had been in parentheses, negative 3, it would have shifted to the right 3 units. That would be a horizontal shift. Okay, so since it's down 3 units, 0, 0 has now shifted down to 0, negative 3. So I put that point, oh, what do you know? That's a point on the circle, isn't it? So it just so happens that that's a point on both the circle and this parabola. What if I shifted 1, 1 down 3 units? Where would I be? Well, 3 units below 1, that's 1 minus 3, or negative 2. So at 1, I was at 1, 1. I went down 3 units, and here I am at 1, negative 2. Similarly, if I went at negative 1, 1, down 3 units, I'm also at negative 2 due to symmetry here. So negative 1, 1 going down 3 units, here I am, and I'm at negative 1, negative 2. So those are like my 3 key points. You always want to have 3 key points for any type of curve that you're graphing. So that's my 3 key points for that parabola. So let's go ahead and draw a quick sketch. It looks something like this, and something like this, with symmetry, hopefully, if you drew it correctly. In fact, if we were to ask, it doesn't look very symmetrical right now, but if we were to ask you for the line of symmetry that you could fold the graph over and it would have the same mirror image on both sides if you had drawn it correctly, that axis of symmetry would have been the line, the vertical line going through the vertex, the lowest point. In other words, the line going through this vertex, 0, negative 3. That would be at x equals 0. So that should have been the line about which you have reflection and symmetry. All right, so with that in mind, what are they really asking when they say to solve the system? We know what the picture looks like, but what do they actually mean when they say solve this system? Well, they are looking for any points where the 2 graphs intersect. So when they ask you to solve the system, they're really saying find all points of intersection. That's really what they're talking about. So if they had graphed it correctly, or if you went on Desmos.com right now and you looked for the points where they're intersecting, those are the solutions you're looking for. It looks like it's going to happen once in quadrant 1, somewhere in quadrant 2 that should be symmetrical on both sides due to the parabolic symmetry. And we already found one of them, didn't we? By accident, using the graph. And that was where that circle, the bottom of the circle and the bottom of the parabola intersected at 0, -3. So actually, I could put that in right now as one of my solutions. 0, -3 is definitely one of the places that is a solution for both of these graphs. How do you think we would find the other 2 points? Well, once we have one of them, we'll have the other one, won't we, due to symmetry? Well, we could use the same approach, substitution or elimination. Now here, you might be tempted to do the same thing we did last time, where you look at y all by itself in equation 2 for the parabola, and you say, well, I'm going to replace y in equation 1 with x squared minus 3. But what would you have to do then to that value in parentheses? You'd have to square it, wouldn't you? You'd have x squared minus 3 to the 2nd power, and that would require you to FOIL and get eventually x to the 4th power, which is higher than currently you know how to solve. Eventually, if you go on in math, you'll learn how to solve degree 4 and higher equations, but for now you don't have those skills. You have degree 2 and lower, okay? So what do? Well, we could still substitute, but we could have to substitute for x squared, okay? So if we substituted for x squared, what I'd first want to do in equation 2 or in equation 1, that's completely up to you, is isolate the x squared term. So on the right side of this equation, we would have x squared by itself by adding 3 to the other side, right? So that's y plus 3, isn't it? Now you could have also isolated x squared in equation 1, in the circles equation. Both of them are correct, okay? So once you've isolated x squared in one of the equations, replace x squared, the entire x squared, in the other equation with what it equals in the second equation, namely y plus 3. So let's do our substitution now into equation 1. We replace x squared with what it equals in the other equation, which was y plus 3. So y plus 3. Here the parentheses are not as important because we're not multiplying that by anything or squaring it. It's just y plus 3. So if you ignored the parentheses here, it wouldn't hurt you at all. Plus y squared, we're still in equation 1, equals 9. Now we have a quadratic degree 2 equation. We know how to solve those. We need to get 0 on one side and see if we can factor or use the quadratic formula. Writing everything in descending order, we get y squared in front. We get the plus y term. Now we have a positive 3. But we also have a 9 that we need to move over as a negative 9 to get 0 on the right. So if you subtract 9 from both sides, that happens. 3 minus 9 is negative 6. We've seen variations of this trinomial before. What would my factors be? For the trinomial, y squared plus y minus 6 equals 0. Well, did you get a y and a y? Good. Different signs. Factors of negative 6, which add up to positive 1 when you put them together. So would this be 6 and 1 or 2 and 3? Well, it would have to be 2 and 3, right? Because they're 1 apart. And we want a positive 3, since we want to end up with a positive 1, y, and we have a negative 2. So this time it appears that when I set each factor equal to 0, my possibilities would be either y equals negative 3 or y equals positive 2. Well, that should be good news, because if you look at the picture, we already knew that when y equals negative 3, they were both at 0, weren't they, for x? And you can verify that if you put in your negative 3 back into the equation with the smaller powers, which would be the parabola. If you put it back up here, your y equals negative 3. What happens if you take negative 3 plus 3? You get 0, and the square root of 0 is 0. So it is in fact true that when y is negative 3, x is 0. But what about when y is positive 2? Plug it back into that equation with the lower powers, the parabola. So now you would say that 2 plus 3 is equal to 5. So x squared equals 5. So if x squared is equal to 5 in that case, what would x have to be? That's right, x would have to be plus or minus the square root of 5. Now for graphing purposes, you could put it in the calculator, of course, to get an approximation. But you could understand just from thinking about it, the square root of 4 is close to the square root of 5, and I know the square root of 4 is exactly 2, right? Similarly, the square root of 5 is less than the square root of 9, which is 3. So I know that this number is between 2 and 3. So without even looking at a calculator, it should make sense that these 2 points, when x is roughly between 2 and 3, our y output should be at exactly 2. So now we know that when y is exactly 2, that is produced by x values of positive square root 5 and negative square root 5. Both of those x values, those inputs, should create outputs of 2. So for these 2 points, you could write them separately as negative root 5 comma 2 or positive root 5 comma 2. Or if you're lazy, you could write plus or minus square root 5 comma 2. So both the positive and the negative square root of 5 as inputs create the output of 2. Okay, so we found all 3 points of intersection by using substitution carefully by isolating x squared and replacing that expression in the other equation. Then we took our answers for y in this case and we input them into the equation with the lower powers, the parabola. Notice that if you had inputted them into the circle, you would have gotten extra solutions that would not be true for the parabola, but only for the circle, which is why you always go to the lower power equation. All right, so we did one together. Let's see if you can do the next one completely by yourself. Example 2. You don't need to graph it this time. It says solve the system if possible using substitution or elimination. The first equation you probably don't recognize. It's okay. It's going to be called a hyperbola later on in math. It's called x squared minus 4y squared equals 16. The second equation you may recognize, it's line. 2y minus x equals 2. So if you're really curious and you want to know what a hyperbola looks like, they end up looking like pairs of curves. Now it could be hyperbolic opening left and right or hyperbolic opening up and down. And you can verify what this one looks like by clicking on the Desmos link provided. But for now, I don't expect you to know that until you move on in math a little bit more. So I do expect you, though, to pick one of these methods and attempt to solve for x and y when the two equations are intersecting. So go ahead and pick your way you're going to try and come back and see how you did. Okay, now if you were trying to pick elimination, you may have run into a snag because you don't have any like terms which would cancel. So elimination wouldn't be appropriate in this case. But the substitution method definitely would. And if you're like most humans, you probably isolated x in equation number 2 in the line. So you would have received the new version of that equation as 2y subtract 2 from both sides, so that now you just have positive x on the right when you add x to both sides. So x equals 2y minus 2 would isolate x in the second equation. Now that you've isolated x in equation number 2, you can replace x in equation number 1. But notice you're replacing only x, not x squared. So what would equation 1 look like after you make that substitution? So let's do our substitution. And again, feel free to pause the video and try it yourself if you haven't already stopped it. So I'm going to replace x with 2y minus 2. And then I'm going to do what equation 1 tells me to do. It tells me I need to square that, then subtract 4 copies of y squared, and that should all equal the number 16. Okay, so we're trying to make these two equations equal each other. We want to see if it's possible, and if so, where. All right, well, if we square a binomial, 2y minus 2 is a binomial, 2 terms, we have to, do you remember what we have to do? It starts with an F, ends with an L, has an OI in between. It's called FOIL. Yeah, we have to multiply the 2y minus 2 times itself. So 2y minus 2, 2y minus 2. If you've done enough of practice with multiplying a binomial times itself, you should recognize the pattern here. It becomes the first term squared because 2y times itself is really 2y squared, or 4y squared, 2y in parentheses squared. 2y times negative 2 is negative 4y, and it happens twice, so you end up with negative 8y. And negative 2 times negative 2 is the same as just squaring the last term there. You get positive 4. Then you have to remember to bring everything down. So bring down your negative 4y squared, as well as equaling 16 on the other side. Okay, now you're very fortunate. Your professor was kind to you in this problem, because something cool happens. You go from a quadratic degree 2 equation to a linear degree 1 equation. How? Because the like terms, 4y squared and negative 4y squared, they wipe each other out. Death to you, death to you. You're now left with a nice linear equation. Negative 8y. I could even move over the 4 by subtracting it, because a linear equation you want to solve by isolating your variable. So 16 minus 4 is really, what, positive 12? And so what we notice here is that we're going to get a fraction. It's okay. We're going to get the fraction because we're going to divide both sides by whatever's touching the variable, right? Negative 8. When I do that, I get y by itself, and now I have y must equal a positive 12 divided by a negative 8. Well, a positive divided by a negative gives me a negative result, and both of those numbers are both divisible by the same factor of 4. 4 goes into 12 3 times, and 4 goes into 8 2 times. So if you said that the y answer, where these two graphs come together, is when y equals -3/2, or -1.5, you would be correct, and you can know you're right by always plugging them back in and seeing if both of them are true, satisfied together. So it looks like if we are going to have a solution, it's going to be at that one location, -3/2, or if you prefer, -1.5. We're not done yet, though, because we need to know the x value where the two of them would intersect. So where do we go from here? We have to plug in y somewhere, but how do we know which equation to plug it into? That's right, we always choose the equation with the lower powers. So in this case, the line. So we substitute back into that line, and we had that 2 times y minus x should equal the number 2. But we've just found y to be the fraction -3/2, -3/2. So multiplying fractions is an essential skill if you're going to be successful in math. Of course, there are calculators that can do this, but if you plan to go on, you need to be able to do this operation by yourself quickly. So remember that 2/1, we can multiply across and then simplify, or we can cancel out any common factors. That's the way I'm going to take 2/2 cancels. I have -3 minus x equaling 2. -3 minus x equaling 2. What that means then, if I have -3 minus x equals 2, I need to get x on one side. You can pick whichever side you like. I'll pick the right side. I add x to both sides, and I subtract 2 from both sides. -3 minus 2 is -5. So I'm getting a result of x has to be -5 in order for y to be -3/2. So let's plug that in as our ordered pair now. -5, -3/2. Or -5, -1.5 is the one and only time where your line and your hyperbola would intersect. And if you have a moment, click on the Desmos link and you're going to see the hyperbola opening left and right and a line touching exactly at that spot. And it's going to be pretty cool to know that you're right. Again, the other way to know you're right, plug in both of those numbers into both equations and make sure that it's true on both sides. It's the same thing. All right, so we've done our examples in this video of how to solve a system of non-linear equations using substitution and elimination. But to really understand what's going on, you have to know how to graph. So make sure you're practicing your graphing skills as well as all of the skills that we've talked about in today's video before I see you next time. All right, remember to practice because math is not a spectator sport. See you then.